Hello, this video will be looking at isentropic process for ideal gas, right? So in the previous video, we have come up three equations to solve entropy change for ideal gas. And so from there, that will segue to this topic, isentropic process for ideal gas. If you remember, when we have those equations back then, we have our, if it's approximate analysis, before we go ahead actually integrate them. After we integrate them, we have those two equations. We have S2 minus S1 equals CV natural log. This is CV at average temperature, natural log of T2 over T1 plus R natural log V2 over V1. So go ahead and look at the previous video if this needs to be reminded. And also we have a second equation, Cp at T average and a natural log T2 over T1 minus R natural log P2 over P1. We have those two equations coming from the method number 1, approximate analysis. But now we are saying if this is isentropic process, if it's isentropic process, in other words, our S2 is equal to S1. So if that equal, what can we come up with? We can come up with from first equation, this is going to be equal to 0, right? So in other words, S2 minus S1 equal to 0. So knowing that, we'll have this equation, CV at this average temperature natural log T2 over T1. That's going to be equal to negative R natural log V2 over V1. And we're going to use our math skills to simplify this a little bit more. So what we'll have natural log T2 over T1. That's going to be equal to minus R over CV at this average temperature and natural log of V2 over V1. And this is going to be equal to, we're going to change that from V2 to V1 to V1 over V2. So then we'll bring this term to be exponent, and get rid of this negative value since we flip those fractions. So that would be R over CV, right? I'm getting rid of the T average. So knowing that, we can get this expression, T2 over T1. That is equal to V1 over V2, R over CV. Okay, what is R over CV? Let's do a quick review on this one, because we know for ideal gas, our R, gas constant, is going to be equal to Cp minus Cv, right? And because of that, if we're going to use divide by Cv on both sides equation, R over Cv is going to be equal to Cp over Cv minus 1. And what's Cp over Cv? That's our specific heat ratio. That's our K value, K minus 1. So knowing that, we can come back to simplify this exponent to be K minus 1. Voila, we have your first equation for isentropic process of ideal gas. So have to be careful. This is for ideal gas, and it's isentropic process. Those are the two conditions. Okay, so imagine if we did this derivation for this first equation, we're gonna get another equation from this equation as well, right? And so here I don't need to derive that one more again, and here I'm just gonna write down another expression, so which will be T2 over T1. That's gonna be equal to, instead of V volume ratio, for this one we're going to use our pressure ratio, so it would be P2 over P1 natural, and here exponent become K minus 1 over K. That's going to be our second equation for ideal gas isentropic process. Those are the two. Okay, so that's the end of this topic discussion, isentropic process for ideal gas. And I can't wait to show you in the next video how we're gonna apply those two formulas to solve problems. Okay, I'll see you then.